I'm sure you've heard the news. In the vast, silent arena of the cosmos, a monumental event is unfolding, a story whispered across light years. Two titans of space are about to clash. This isn't just a collision, it's a confrontation between the most extreme objects the universe has ever forged. On one side, a shimmering, hyperdense corpse of a star. On the other, a rupture in the very fabric of space-time itself. This is the ultimate showdown, a neutron star versus a black hole. What happens when an object made of the densest matter imaginable meets a force of pure, inescapable gravity? The outcome is far from simple, and the journey to the answer will take us to the very edge of physics, where the rules of reality are pushed to their absolute limit. Let's meet our first contender, the neutron star. This isn't a star in the traditional sense. It's a stellar zombie, the leftover core of a massive star that died in a spectacular supernova explosion. After the outer layers were blasted away, the core collapsed under its own immense gravity. Protons and electrons were crushed together to form a sea of tightly packed neutrons. The result? An object of almost unimaginable density. Imagine taking the entire mass of our Sun, a body over 1,000,000 times the size of Earth, and squeezing it into a sphere just 20 kilometers, or 12 miles across. That's a neutron star. It packs a sun into a city. A single teaspoon of its material would weigh over 1,000,000,000 tons on Earth, as much as a mountain. This crushing density is held up against gravity's pull not by heat or fusion, but by a bizarre quantum mechanical principle called neutron degeneracy pressure. It's a cosmic standoff where matter itself says, no further. But density is just the beginning of its powers. Neutron stars are born spinning, and like an ice skater pulling in their arms, their rotation accelerates to incredible speeds as they collapse. Many spin hundreds of times per second, creating what we call millisecond spins. This rapid rotation, combined with their super-dense conductive interiors, generates the most powerful magnetic fields in the universe. We're talking mega-magnetic fields, a quadrillion times stronger than Earth's. These fields are so intense they can warp atoms and channel superheated plasma into powerful beams of radiation that sweep across the cosmos like a lighthouse. When these beams point toward Earth, we see them as pulsars, the universe's most precise clocks. So, the neutron star enters the ring as a spinning, hypermagnetic, ultra-dense juggernaut, and in the other corner, our second contender, the black hole. If a neutron star is the corpse of a star, a black hole is its ghost. It's what happens when the core of an even more massive star collapses, and nothing, not even neutron degeneracy pressure, can stop it. Gravity wins. The core collapses infinitely, crushing all its mass into a point of zero volume and infinite density, known as a singularity. Surrounding this singularity is a boundary called the event horizon. This isn't a physical surface, it's the point of no return. Once you cross it, the gravitational pull is so immense that the escape velocity exceeds the speed of light. And since nothing can travel faster than light, nothing escapes, not even light itself. Black holes are defined by just three properties: mass, spin, and electric charge. They are the ultimate minimalist objects. While a neutron star is a complex ball of exotic matter, a black hole is pure, warped space-time. Its power isn't in what it's made of, but in what it does to the universe around it. Its insane gravity bends light, warps space, and slows time. It doesn't have a magnetic field of its own, but the material it pulls in, its accretion disk, can become superheated and generate powerful magnetic fields and jets of its own. The black hole's strategy is simple and undefeated. Gravity wins everything. It is the undisputed champion of gravitational force. So the stage is set. Two titans of space locked in a gravitational dance, spiraling closer and closer together. This isn't a hypothetical scenario. Astronomers have observed these binary systems, watching as they lose energy by emitting gravitational waves, ripples in space-time, and inch toward their inevitable collision. The final moments of this cosmic dance are where the real action happens. The question is, what kind of action will it be? A quick, clean knockout, or a messy, spectacular brawl? The answer depends on a crucial factor: the mass ratio. How much bigger is the black hole than the neutron star? Let's consider scenario 1, the clean swallow. This happens when the black hole is significantly more massive than the neutron star, say 10 times its mass or more. In this case, the black hole's gravitational dominance is absolute. The neutron star's own incredible density and structure are no match for the sheer tidal forces near the event horizon. But because the black hole is so large, its event horizon is far from the central singularity, and the gravitational gradient is actually gentler at the edge. The neutron star can spiral all the way to the event horizon and be swallowed whole before the black hole's tidal forces have a chance to rip it apart. For any observer, the neutron star would simply approach the black hole, its light redshifting into oblivion, and then vanish. The collision would be almost silent in the electromagnetic spectrum, no flash of light, no explosion. The only signal would be a final, powerful chirp of gravitational waves as the neutron star crosses the point of no return. A quick, clean victory for the black hole. But what if the fight is more evenly matched? This brings us to scenario 2, the tidal disruption. This occurs when the black hole is smaller, perhaps only a few times the mass of the neutron star. Here, the gravitational gradient near the event horizon is much steeper. As the neutron star gets close, it experiences an extreme tidal force. The side of the neutron star closer to the black hole is pulled much more strongly than the far side. This difference in force, known as the tidal force, stretches the neutron star. At a certain point, called the Roche limit, this stretching force overwhelms the neutron star's own gravity and the quantum pressure holding it together. The star is violently torn apart. This is where the fireworks begin. A huge amount of super-dense neutron matter is flung into orbit, forming a massive, hot, and chaotic accretion disk around the black hole. In a collision, this neutron matter might glow. As it swirls into the abyss, friction and magnetic forces heat it to billions of degrees, causing it to shine brightly across the electromagnetic spectrum, from radio waves to gamma rays. This could produce a short gamma-ray burst, one of the most energetic explosions in the universe. But not all the matter is doomed to vanish into the hole. Some of this neutron-rich debris can be ejected outwards at incredible speeds. This ejected material becomes the crucible for creating the heaviest elements in the universe. Through a process called rapid neutron capture, or the R process, the free neutrons are rapidly absorbed by atomic nuclei, building them up into elements like gold, platinum, and uranium. These newly forged radioactive elements then decay, heating the expanding cloud of debris and causing it to glow. This afterglow is called a kilonova, an explosion 1,000 times brighter than a standard nova. It's a cosmic fireworks display that can be seen across the universe, a visible testament to the violent creation of precious metals. So in this scenario, the neutron star loses the fight, but it goes down swinging, putting on one of the most spectacular light shows in the cosmos. This isn't just theory. We have seen these events. On August 17, 2017, the LIGO and Virgo gravitational wave observatories detected ripples from the collision of two neutron stars, an event that was followed by a kilonova and a gamma-ray burst, confirming our models. And in 2020, we detected GW 2005 and GW 2015, the first confident observations of black holes swallowing neutron stars. These events provided real-world data, allowing us to test our understanding of gravity, matter, and the universe's element factories. One particularly mysterious event, GB190814, involved a black hole colliding with an object of about 2.6 solar masses. This falls into the mass gap, too heavy to be a typical neutron star but lighter than any known black hole. Was it the heaviest neutron star ever found, or the lightest black hole? The universe still holds its secrets close. This cosmic clash raises fascinating questions. Could a neutron star ever win? In a direct collision, no. The laws of gravity are absolute. A black hole's event horizon is a one-way door. However, a neutron star could theoretically survive an encounter if its orbit was just right, allowing it to be flung away in a gravitational slingshot. But in a merger, the black hole always consumes the neutron star. Another question: what happens to the neutron star's powerful magnetic field? As the star is torn apart, its magnetic field lines would be stretched, twisted, and tangled within the new accretion disk. This could amplify the disk's own magnetic fields, potentially helping to launch those powerful jets of a gamma-ray burst. The star's magnetic energy gets added to the chaos before its source is extinguished. So, who is the ultimate winner? In the end, there's no ambiguity. The short answer is that black holes hold the ultimate upper hand. Gravity is the final arbiter. Whether it's a silent swallow or a violent, shredding disruption, the neutron star is consumed. The black hole grows slightly more massive, its event horizon expands, and it continues its silent reign. The neutron star, for all its density, spin, and magnetic fury, becomes just another morsel, its matter crushed out of existence or added to the swirling chaos around the victor. But the fireworks? That's the neutron star's legacy. In its final, violent moments, it can outshine entire galaxies, forge the universe's heaviest elements, and send ripples through the fabric of space-time itself. The black hole wins the battle of existence, but the neutron star wins the battle for spectacle. It reminds us that even in the face of total annihilation, there can be a final, brilliant burst of creation.